Well, hello guys. Glad that you joined. So, do you have any questions, or you want me to go over some things that I want to tell you guys? I thought
Uh,
maybe we can go over some specific questions that you might have, just in case other people join in and want to see what I have to say.
uh, I think I have a lot of questions between your class and the comprehensive exam. Every type of test we've gone over in class, will they be the only test? Um, will they be the only test covered on your final and or the comprehensive exam, or can they throw in another test that we haven't covered yet?
All right. So, to be honest, I'm not privy of the information of what they put in the comprehensive exam.
Hmm.
Only a couple of things that I might know is because my students come back later and tell me that okay, some of the things that you covered were in the exam, and I knew them because it was in the class. I think ANOVA is there for sure. Regression might be there. So everything that I
Yeah.
cover would be in the list of what they would pick.
Okay. Yeah.
Okay. I'm not sure if they cover anything that I don't cover. Maybe
Hmm.
I'm not sure if they cover logistic regression, but in this years that I'm teaching online, just 8-week classes, I haven't heard anything that they ask logistic regression. So that's why I haven't covered it. But that's not only why I haven't covered. I haven't covered it because there's not enough time, in the class.
Hmm.
One just the regression for 1 week is enough. I would say to add logistic regression, you need at least 2 more weeks. So maybe you need
Yikes.
about 3 weeks to cover bivariate regression, multivariate regression, and also logistic regression. So I think everything that I cover would be in the list that they pick.
Okay.
Yeah,
Fair. I appreciate that. Thank you. I
no
mean, even
problem.
in this 8 week course, it's obviously very condensed, and it's still a lot to take in when statistics is hard enough by itself.
Believe me, I understand. I've been teaching this course since 2010. Then I switched to undergraduate statistics 250, and then I went back to
Hmm.
CRJ 716. So when I was teaching a regular semester, I covered more. So I covered logistic regression, but now because I think a lot of students are taking online classes, especially the 8-week semesters. I don't think that you know that logistic regression or Bayesian, any Bayesian tests would be covered, or would be in the comprehensive exam. But like I
Okay.
said, I really don't know
No, I
because
understand.
I don't get
Yeah.
those questions, and I don't know who creates them. Really,
Well,
yeah.
reading from some of the past Comp 716 old tests, they they give you like a data set and everything, and they ask you what's the most correct test to use. Um, so obviously you have to know what is the correct test to perform for the correct data output.
So that is a really good question, and that should be in the comprehensive exam. That for sure should be because that is fundamental in statistics.
Yeah.
And you need to know based on the level of measurements. If you remember from the first week, I stressed
Hmm.
the levels of measurement. Um, Let me see if I can show again application or screen. Even in the assignments of week one, we went over this class survey just to make sure. This should have been done in 715 actually, and I think it probably was.
Mhm.
So how do you get the variables? You get the variables from questions, in a questionnaire or in a poll or in anything. So you get all these questions. So what do they now create? What is the output? These questions now become what? Become variables. Share this other screen. Okay. And now I think you can see the SPSS file, right?
Yes.
So all of the students who took this, here there are both sections actually, your section and the other one that I'm teaching this semester. So what do you see? On top, you have the variables, right? These variables were the questions. So these questions, gender is gender here. Party affiliation or county is somewhere over here. So all of these questions become the variables. And then now the answers given by each of the student become the observations. So this is student 1, student 2, student 3, 4, 5, and so on, 40 something students in both sections. So these are individual answers. So for gender, this one answered female, this one answered Republican, age 25, graduate 4.0, and so on. Okay?
Hmm.
And these variables now have their levels of measurement. You can see the measures right over here. Is it ordinal, nominal? Now, scale is a numerical variable that includes interval or ratio, but they don't have, SPSS doesn't have interval or ratio. They just call scale because there's not much difference actually in the SPSS between those two. But nominal and ordinal, there is a difference. And you know that the ordinal has one more property than the nominal, and that is the ranking and the difference between the categories. Okay? And all I'm doing this introduction is to answer your questions that what kind of test are you going to do? And that depends on this levels of measurements of the variables. Okay? Why it depends on those?
Hmm.
Because as you've seen, if you have a bivariate analysis between two scale variables, what do you have? You have a relationship of those points. Okay? Um, and that relationship, one second, let me just get this out. And that relationship, right? If you plot it into a graphic, x and y, then you'll see a scatter plot, right? Where one dot is convened by the value of x and value of y. And then you'll see that if there is a straight line, there's a positive and strong correlation. If the dots are scattered all around, that's not such a strong relationship. That's a weak relationship. So if you have two scale variables or more than two variables that are numerical in nature, then what tests are you going to do? Right now, you know that you're going to do correlation and regression, right?
Hmm.
You can't do a t-test with two scale variables. You can't do an ANOVA with two scale variables. Also, you cannot do a chi-square or a cross-tabulation with two scale variables. I mean, SPSS will give you some output, but that's not going to be meaningful. Okay. So you have two variables, and you have the x and the y. All right. And then you have variable 1, variable 2, and you have the values. All right. Whatever number of the sample size. So if you take the first pair, you're going to see that, for example, V1 is the independent variable that goes into the X. X is always the independent variable, and V2 is the dependent variable, so that there's a relationship between these two where one might affect the other. So you take the first two numbers. So for example, 2 and 4. So you see 1, 2, you see 1, 2, 3, 4. So you might get a point value here that is the intersect of 2 and 4. And this could be probably 5 and 3. So 1, 2, 3, 4, 5, and 3. 5 and 3, you would have another point here. And then you might have a lot of points, okay? So there is a scatter plot here. So what kind of tests did you do with these two numerical variables? You did correlation and regression, okay? Where one variable is correlated with the other, and then you have a correlation coefficient R that is from 0 to 1 or from 0 to -1. Okay, that is a positive correlation or negative correlation, or a regression. With a regression line, the least square line, right? And then you see that this is the slope and this is the intercept. And then you create that equation, the regression equation. So the slope would be for 1 unit increase. What is the increase or decrease in the dependent variable? So 1 unit increase in the independent variable of the predictor would cause this much increase. So that increase would be this difference, right? From here to here. So you see, as that goes up, that's the difference of going up from 1 unit to the next. But anyway, the question was, what kind of tests are you going to do? So you're going to do a correlation and regression. All right. So if you have now one categorical and one numerical. So categoricals are nominal ordinal, and the other one is numerical. What kind of test are you going to do?
That's going to be a t-test.
Correct, but partially correct. Why?
Well, okay, so can you repeat it again?
No, you got it. You understood it.
Is it the,
and I'm
is
going
it
to
the,
repeat.
okay.
Uh-huh.
Is it the independent samples t-test?
It could be independent samples t-test or a paired samples t-test, but it could be something else too. And all depends on
The number of variables, right?
no, the number of groups in the categorical variable.
Number
So
of
if you
groups
have two
could be an
groups,
ANOVA, right?
exactly. So if you have two groups, let's say male and female, and you have the age here and age for females here, then you're going to get the mean of age of males and mean of age of females, and you're going to compare these two. So you see, you need to figure out if there's a difference. For those of you who don't live in Brooklyn, that's what happens here. Did you hear that?
Sure did.
So then you compare the differences, and you figure out through the t-test. Why t-test? Because there are two groups, that this difference is significant or not. Okay. This is independent samples t-test because you have males and females. The paired samples t-test is before and after, but it's the same people or the same units of analysis or the same observations. Let's say the weight of some sample of people before they entered into a Weight Watch treatment, and then 3 months later they get the weight again. So they have a paired sample here, and then you do the paired sample, and then you figure out the mean for before, mean for after, and you see if there's a difference there, and if this difference is significant, and then figure out whether or not this program worked. All right, so that's the paired sample. Now, if you have more than 3 groups, group 1, 2, 3, and 4, then you do ANOVA. Okay? So one categorical, one numerical. Do we understand this? So you have to figure out whether or not this categorical variable has only 2 categories or more than 2, 3 or more. Because on that particular thing, it depends whether or not you're going to do a t-test or no. All right. What if you have 2 categorical variables? What kind of test are you going to do? 2 or more, because we have bivariate analysis where you have 2 variables, or we have multivariate analysis where you have more than 2.
Is that the chi-squared t-test?
Yes. And, well, no. It is chi-square, but chi-square, could be probably appropriate in Starbucks, right?
Chi-square.
Yeah.
Sorry, I couldn't remember how to pronounce it.
Just remember Starbucks and then you'll know.
Yes.
So not like Starbucks. It's not a chai or tea, it's a chi. So it is chi-square, and that's the test. Chi-square is the test, but you also can do the cross-tabulation, which is the table where the variables are contingent upon each other, and then you see the relationship between them. Right? So these are the tests. All right, there are some more, but we're not going to do those, and those are for very advanced. Oh, by the way, this is a t-test a lecture that I've done with another class a few semesters ago when I was teaching the regular class online when the pandemic hit. Anyway, so the t-test. How to interpret the independent samples t-test output. Let's check it out. So it's right here. First, you have to look at the equality of variances. Like I said, if the equality of variances just means that the distribution is normal, the variances or the variation between the values are normal, right? On both sides, on both groups. So we look at the Levene's test for equality of variances. And we have this significance right here. Now, if the significance is greater than 0.05, well, first of all, we look at the significance that is smaller than 0.05, where we have to reject the null hypothesis. But this significance here is not smaller than 0.05. Therefore, we don't reject the null hypothesis. And the null hypothesis is that the variances are equal. And if we don't reject that, we assume that equal variances, that this distribution has equal variances. And if this was smaller than 0.05, we reject the null hypothesis of equal variances. Therefore, equal variances are not assumed. We have to go to the second row. In this case, because this is greater and we don't reject it, we go to the first row and we look at the significance two-tailed. And look at that. That is a small number. It's not 0, never is 0. But it's smaller than 0.05, our threshold, our alpha probability level that we create always to minimize or eliminate type 1 error, that we reject a null hypothesis when it's true. Okay, and what that tells us? That tells us that we have to reject the null hypothesis, the real null hypothesis, not the hypothesis of the equal variances. That is a small hypothesis within the t-test. But the real hypothesis is, what is it? That the mean of the two groups, right, is the difference between the means of the two groups that I showed you in the whiteboard is statistically significant. That's all it shows. In that case, for example, the mean age of males and females are different, and that difference is statistically significant. That's what the test shows. Okay. Another thing to look at, not only in the t-test but also in ANOVA and regression, is to look at the 95% confidence interval with a lower bound and upper bound. What it means is that if we did this sample 100 times, 95 times this mean difference, which is right here, 1.5, okay, will be between 1.2 and 1.8. So we are confident enough, at least 95%, that this mean is not going to be under 1.2 and is not going to be over 1.8. Now, if we were not confident, then the 95% confidence interval of the difference would have opposite signs. So if they cross zero, that means that we're not confident. This mean could go either way. Either males would be older on average or females would be older on average. And if we can't tell, then we have to retain the null hypothesis that there is no statistical significance, or that we have no evidence that there is any meaningful difference in the mean of these two groups. Does it make sense? Or is it too much for 10 minutes?
Slowly.
Okay. So anyway, this is the t-test. You're going to have the t-test in the final. So make sure that you know what's going on here. Okay, so that's this diagram that I created. If this is greater, look at equal variances assumed, and then look at this p. If this is smaller or equal to 0.05, then look at the second row, bottom one. Okay. Next. Let me show you a quick t-test here. First of all, let's see gender. Gender, female and male, and then we have age, right? Two groups. Age is a numerical variable, so we have to do a t-test. Let's look at the value labels. Okay, so one is male, two is female. We need these two value labels and values because we need that for the t-test. Okay. So when you go to analyze, okay, you go to compare means, and then you go to independent samples t-test. And that's another thing. Independent because males and females are independent of each other. Paired samples t-test is when usually there is the same set of people, of unit of analysis, but you have two measurements, one before and one after. So they are paired. So you want to show any difference between any effect that something worked or didn't work. Maybe a weight loss, measurement of weight before, 3 months later, another measurement of weight, and see if that particular thing worked, whatever that is. Okay, so that's the difference between independent and paired. But anyway, in this case, it's independent samples t-test. We have gender, that's the grouping variable or independent variable. We put it there. We define groups by group 1 is 1, group 2 is 2. They could have been 0 and 1, could have been 10 and 9, whatever numbers you assign here, but 1 is male, 2 is female, so that's what we're going to put. And then age goes into the testing variable. Do we need any options? No, because usually it's 95% confidence interval, which translates to 5% alpha or probability level that we compare our p-value here. Yeah, we need the estimate effect sizes because this goes hand in hand with the p-value, okay? And also with the conclusion about the null hypothesis. I'm sorry, the decision about null hypothesis and the conclusion about the alternative hypothesis. So we click OK. Pretty quickly, we look at the independent samples table is not produced. Samples is not produced. Okay, I knew something was wrong. And it doesn't work. Why? Because even though the student put the value labels 1 and 2 for female, she did not put it over here in the gender. Why? Because you see, as it didn't work here. Okay, 2. You have to check now everything. Come on. Work. Because SPSS doesn't work with characters, it works only with numbers. That's the problem. All right, 2. You know what? I'm just gonna copy this. Wherever I have female, I'm gonna paste it. Female, female, paste it there, paste it there. By the way, you can see how you work with SPSS. And I see that everybody, not everybody, I haven't looked at, but just a few are not working. A lot of you are working, the majority. And those who are not working, maybe they can look at the career in statistics in SPSS. There are a lot of positions for research assistants, and the federal government is short in statisticians, you know. Anyway, so look at this. See now, this toggle button right here, 1 and A, toggles between the values and value labels. So value 2 is female, value 1 is male, female, male. Okay, now if I do the independent samples t-test, I'm going to do OK because I have everything. Now it's going to work, you see? So we have 6 males, 40 females. Males have a mean age of 34.17. Females 27.78. That's right here in the mean difference, 6.39. All right. Look at this. Some people, you know, it's easy to just go to the two-sided p-value and then look at this p-value and say, okay, this is greater than 0.05, so we fail to reject the null hypothesis. But you need to report it. So which one are you going to report? Tell me. 0.122 or 0.154?
122.
Why?
Because the F, it's above the 0.5.
No. Well, you're right. That is 1.22. I'm sorry, 0.122, but not because of the F. It's the significance. So this is greater than 0.05 because the F could be under 0.05 and you'd make a mistake. And the significance might be greater than 0.05. But you look at the significance. Always look at the significance in the test table. Okay. So because this is greater, we fail to reject the Levine's null hypothesis. So we assume equal variances. Therefore, we look at the p-value there, two-sided, okay, because our alternative hypothesis was two-tailed, that there is no significant difference between the ages of males and females. If you had created a one-tailed alternative hypothesis that males are older than females, then you'd look at this. But sometimes, not sometimes, most of the times, this will mislead you. So always create a two-tailed alternative hypothesis that there is a significant relationship, or there is a significant correlation, or there is a significant difference. Okay? So what do we say here? Reject the null? No. We retain the null, fail to reject it, and we say that. And also, the conclusion has to be worded in terms of the alternative hypothesis. So when you fail to reject the null, I know it's like a play of words, but you have to do it that way. So because the alternative hypothesis is your idea, is your research hypothesis. So you want to prove that right. But can you prove it right? You can prove it right if you prove null wrong. So if you reject null, you prove yours right. But in this case, we cannot reject the null. Therefore, our hypothesis, research, in your mind, click research equals alternative hypothesis. And then you say, we don't have enough evidence to accept the alternative hypothesis that there is a significant difference between men and women in terms of their mean age. And I'm kind of surprised, actually, because this mean age of 6.5 years should be significant. But that's the beauty of statistics. You can have a rejection, you can have a retainment of null hypothesis even when that is false. Okay, and that is a type 2 error. Now, why that happens? That happens because we don't have enough sample size. We don't have enough people. See this? We have only 46 people here. If we had probably 460, 10 times more, then we might have been able to see that the difference now is significant. In this case, it's not. But in this case, in another case with more people, would be significant. And especially the sample size for male. It's so much disproportionate that it might give you this p-value. So in this case, this is beyond simple statistics, though, and it's worthy of graduate students. So you have to know this. Look, the lower and upper have opposite signs, so it means that it's not significant. That goes hand in hand with the p-value, and that's why the p-value is not significant, because there is opposite sides. It could be the mean age could be negative, the mean age could be positive. So you're not sure, therefore there's no significance there. And now, what we need to see, can we conclude just because of this? No, because you already see that there is a small, very small sample size that might yield a wrong p-value. So what do you see next? Next, you see the point estimate of Cohen's d. Look at from 0 to 1. There's almost 7. 0 to 3 is small effect. 3 to 5, medium effect. 5 to 10, significant effect. So even though we failed to reject the null hypothesis, we did not accept the alternative hypothesis, this mean difference has an important effect. So if you have such a test in front of you, okay, and most likely when you have a p-value that is greater than 0.05, always make sure to do this, the sample effect, the Cohen's d, because that would give you whether or not that difference was important, even though it was not statistically significant. Let's do an ANOVA. I want to figure out whether or not motivation for doing a master's degree really has any effect on, let's say, graduate GPA. Maybe somebody who is doing this for a career advancement, is really motivated and will have a higher GPA than the others. We'll see. And now, why is it ANOVA? Because there are more than 3 categories in the independent variable. 3 or more than 2. So let's do analyze, compare means. Then we go to one-way ANOVA. And what do we do here? We find graduate GPA. Graduate GPA is the dependent list, is the outcome. What is your motivation? Is the factor. We do need effect sizes, of course. We do need the post hoc. I usually go with Bonferroni. All right, continue. Options, make sure that you get the descriptives. Homogeneity of variance test it's like the Levene's test, but here is not done automatically like in a t-test. You have to select this. And Welch test. By the way, Welch is more robust than Braun Forsyth. I know that most of you answered correctly on the discussion board about this question. I want a mean plot just for visualization. Level is 95%. 1 minus alpha is 5%. 1 minus 5% is 95%, so that's confidence interval. Continue. Click OK. And let's check this out. Let's look at the descriptions. First of all, we have 1, 2, 3, 4, 5 categories. 2 categories were added, and they have only 1 student. So that would kind of skew the variability or the normality of the distribution, because you can't have a difference when you have only 1 value in 1 group. So look at that. Career advancement, motivation, students have the lowest mean of a graduate GPA. Career choice, higher. Personal satisfaction, higher than the first, but lower than the second. And the other 2 lonely answers here have a real high GPA compared to the others. Let's see if this is significant. First of all, we test the homogeneity of variances, and we look at the significance is 0.089. If we round up, that is greater than 0.05. Therefore, we fail to reject the null hypothesis of variances are equal. Variances are similar or equal. So if we reject that they are not equal, that means that they are equal, and that's why you conclude that the assumption is met, that variances are equal. If the assumption is met, then ANOVA will do. If this was smaller than 0.05 and the homogeneity of variances assumption is not met, then you had to go to Welch test, not this. But because this is greater than 0.05, then ANOVA is perfect. You see a significance of 0.735. That's really high. Now, what happens to the null hypothesis that there is no significant difference between the mean graduate GPA of students with different motivational categories? Do we reject that, or we fail to reject?
We fail to reject?
Yes, we do. So if we fail to reject, the null hypothesis stands, and the null hypothesis says that there is no significant difference. So we don't accept the alternative hypothesis, and we say that we don't have enough evidence to say that the mean differences are significantly different. So they're not. They're not different. So all of these categories, on average, as a whole, they're not different. And also the scale, the effect sizes here, the point estimate is small, so it's not really, it doesn't have an important effect. The Welch is not produced because the ANOVA is correct. Look at this now. This is the mean plots. 3 or more categories. Motivation for criminal justice master's degree, right? Has more than 3 categories, correct? Okay, perfect. Let's look at ANOVA, right? Analyze, compare means one-way ANOVA. So the dependent list is the numerical variable, right? The numerical variable is the dependent variable. So that is motivation. All right, cool. Factor is the independent variable. I'm sorry, this motivation is the factor. And graduate GPA is the numerical variable, is the dependent variable. Post hoc, we do need this to see the difference between each of the pairs of the categories. So I usually do Bonferroni, but there are other things. If you want to do, for example, Gabriel or Duncan, you can. Gabriel is usually done when there's a lot of discrepancy between the numbers of values of each categories. But I'll do Bonferroni for now. That's a robust test. Options, I want descriptives. I want to see homogeneity of variance test if variances are equal, kind of like the Levine's test. But I want to do Welch. Welch is more robust than Brown-Forsyth test. Okay. I want a mean plot just to look at it. Level 0.95 correspond to 5%. Cool. I don't want to do any bootstrapping. I want the effect size, of course. By the way, have you looked at what this paste does? This just does the syntax. Opens up a syntax output, and then you can, if you know exactly what you have to write, for example, statistics, and then some other code, like in SAS, you can, and then you hit this arrow, and that is run. Anyway, I don't want that right now. Oops. Oh, man. One-way ANOVA. Everything is there. Click OK. Let's look at this now. First of all, and by the way, have you seen that I've asked SPSS to give me APA-style tables in Times New Roman? I put a screenshot in the I think in week 6. Did you see that? How you can make this? I'll show you anyway.
Yeah, I'm sorry. Can you show that one more time, Professor? I'm sorry.
The ANOVA? Or how
no,
to
just
do
how
this?
you made the tables into the APA format.
Okay. that is a process with the options in SPSS, not with the test itself. Okay, because every test that you run otherwise will be will be in APA style in this format. Okay, but I'll show you right now. Click Edit. You go to Options. Okay, it opens up this table dialog box. First of all, do you want to display labels or names? Names are short names of variables. Names are these right here, and labels are the ones that are longer, that you kind of describe what it is. I'll do labels. I want to do alphabetical so that it's easier for me when I know the names of the variables to find them, even though that doesn't really matter. I'll do apply. Okay, so that's done. And then I go to pivot tables. This is important. So do it with me if your SPSS is open. So go to pivot tables and now scroll down to find APA Times Roman 12 point. SPSS did not have this before, so they just put it here. Usually before I used to do academic, which is kind of close to that. And then I used to change the format, the text into Times New Roman. But now it's so easy. APA Times New Roman, that's it. Click this shrink width to fit, so that longer table, like the one that is wide, like the t-test table, is going to shrink to fit whatever. When you export it into Word, it fits into the Word perfectly. That's good. So that's how you do it, and you do OK, all right?
Thank you.
You're welcome. And so now we go to output. So what do we see? We see the mean, what was our graduate GPA? So those students who had as a motivation for the master's degree career advancement actually had a smaller mean, lower mean in the graduate program. But career choice had bigger than that. All those who did it for the family really were motivated, I guess, because they had higher GPA. Personal satisfaction, a little bit lower, but still bigger than career advancement. To be better prepared for the future speaking I'll be doing. But that's only one here, and then my family is only one. So they don't really have any variability. We'll see how significant that is. So test of homogeneity of variances. Are the variances equal? Yes, they are. Look at the significance. Greater than 0.05. So the variances are equal. We assume equal variances, right? Therefore, the ANOVA significance works. If this was smaller, then we would have resorted to the what? Welch test. But Welch doesn't really work here now because ANOVA works well, okay? Anyway, what does this significance mean? Fail to reject or reject?
Fail to reject the null hypothesis.
Fail to reject null hypothesis. Retain, yes. So what does that mean? We don't have any evidence that there is a significant
There's
difference.
no statistical.
That's correct. No significant difference. What about effect size? Not really. It's very small. So yeah, this stands. This is a good test. Look at that. From low, up, up, down, up. Yeah, this looks like a no significance. But anyway, this means plot is really good. Now, one other thing. So how are you going to take this APA style table from here and put it into Word? This is ANOVA. So I do copy, go here, and then right click, paste. All right, this is table 2, ANOVA test of mean difference of grad with GPA and career motivation. All right, so you have to do a descriptive table name, and that's it. This is good. But some students, when they paste here, is not a table. Okay, it's an image. And when they have pasted into the discussion board, I have seen just very small table, and I couldn't really see it. So how and why that happens? When you go to to the output, right click, and then you do copy special, write that down. A new dialog box opens up, and then they have this image clicked and nothing else, or image and meta file, for example. So unselect image and select plain text, rich text, Excel worksheet. And then this is going to copy as a table and not as an image. Okay, so that's a secret. That's good. So these were the kind of things that I wanted to talk to you about, and now I want to go to the final. All right, let's go to the final. So in the final, have you seen this sample final?
Yes.
Okay, that's going to be the format that the final will be. But
Yes.
There's going to be more questions, of course. So you're going to have a question on the t-test, one question on ANOVA, 2 questions on one on crosstabs and one on chi-square. They're kind of both the same, but you need to be able to do that. So you can't write anywhere, you see, only in the respective fields. So, right? No, okay. So, for example, when you open up GSS 2012 revised.sav, I'll give you the names of the variables, all right? The names of the variables will be this and that. So you're going to see and put now which one is the independent variable and which one is the dependent. Right now I don't know, but I'm just going to put these there. So that's how you're going to fix it. You're going to fill this out. Level of measurement, what is this? You're going to say ratio, for example. All right, don't take my word for it because I really don't know. I'm just going to, pretend that this is it. Dependent variable is nominal, whatever. What is the distribution? Is it normal or somewhat normal or not normal? How are you going to figure that out? You're going to figure that out based on this SPSS Kolmogorov-Smirnov test for normality. It's an easy test. You can do it. You're going to have a lot of time to do this. So take your time and do this right because it's 30 points. You see, I'm asking, put the null hypothesis, alternative hypothesis, which test you're going to do and why, and observe whether now variances are equal, right? Homogeneity of variances. Now, right away, you can figure this out, right? That this is going to be ANOVA because it's homogeneity of variances. We talk about that only in ANOVA. And produce a post hoc test and explain what you see. Calculate the effect size. Now with SPSS, SPSS can calculate it for you. If not, you can do the calculation by hand. It's in the textbook. I think you can, the equation is there. And again, you're going to have a lot of time, enough time to do this. So, but don't leave it for the last day. So anyway, what I was trying to do is right click and paste that as a table. Look at that. Isn't that nice? Now, of course, you have to remove this column. Delete cells, delete column. And why do you remove the column? Because you don't need the significance in the APA. If it was significant, then you would put an asterisk. If it's significant at 0.05, or 2 asterisks if it's significant at 0.01, and you would say here P smaller than 0.001. Sorry, 0.1. Okay, if it's only 1 asterisk, then you say 5. But in this case, it's not significant, so you don't do that.
May I ask?
And you already know how to put the interpretation in APA style, right? And don't just say only one sentence. That's really not cool and not professional. Talk about it. Rejection of the null hypothesis because the p-value is smaller than 0.05. Put the t-test there or the f-test there with the degrees of freedom in parentheses equals 0.502, comma, p greater than 0.05. Because we failed to reject the null hypothesis, we don't have enough evidence to accept the alternative hypothesis that such and such and such. Okay, so make it like, you're telling the reader what this really means. Okay.
Professor?
Yes.
Are we, the sample final, is that part of our homework? Are we turning that in, or it's just for practice for us?
It's just for practice.
Okay.
It's just
If we
for
turn it
practice.
in though, or are you at some point going to give us the correct answer so we can compare it?
Of the final?
Just the sample that you gave
No.
us. If no,
No. They because it doesn't really make any difference if I give you answers to this or not, because I've already given the answers to the discussion board. Have you been able to look at all of those?
oh yeah, absolutely.
For example, the ANOVA, that's the discussion board. So this whole thing, I didn't expect everybody to write all this much, but it's good for you to know. Then how did we get this in ANOVA, all of that, to use or utilize ZTNF Excel file, rejection region, and then the test of the ANOVA for the different streets in London about murder rate and all that stuff. You see? So the answers are here.
Yeah, can you, I don't know where to find that. I'm sorry.
Which one?
The answers that you give, because in my other classes I've found it under the grading stuff, but that's just mine. So I don't know the category under Blackboard to find those answers.
Oh, they are in the respective assignments folder, right where the assignment was, right where the discussion board was. That's where the answer will be. All right, so I made it easy so that, in ANOVA, for example, you go to assignments, and now the discussion board is not there anymore because people are not allowed to submit the answers to this when the answers are already given. So that's where you have week 3 discussion board. For week 5,
I wasn't tracking
again in the assignments, discussion board answer for 5. Anything that comes to mind, or we can then end this session. And if you have any questions later on, if you think of anything, you send me an email.
Thank you. Thank you.
All right, you're welcome, and good luck in the final.
Thank you.
And again, like I said, just email me if you have any questions. Bye, everyone.